Isidor Isaac Rabi was a Polish-born American physicist and Nobel laureate, recognized in 1944 for his discovery of nuclear magnetic resonance, which is used in magnetic resonance imaging. He was also involved in the development of the cavity magnetron, which is used in microwave radar and microwave ovens. Born into a traditional Jewish family in Řymanice, Galicia, in what was then part of Austria-Hungary, Rabi came to the United States as a baby and was raised in New York's Lower East Side. He entered Cornell University as an electrical engineering student in 1916, but soon switched to chemistry. Later, he became interested in physics. He continued his studies at Columbia University, where he was awarded his doctorate for a thesis on the magnetic susceptibility of certain crystals. In 1927, he headed for Europe, where he met and worked with many of the finest physicists of the time. In 1929, Rabi returned to the United States, where Columbia offered him a faculty position. In collaboration with Gregory Bright, he developed the Bright-Rabi equation and predicted that the Stern-Gerlach experiment could be modified to confirm the properties of the atomic nucleus. He developed techniques for using nuclear magnetic resonance to discern the magnetic moment and nuclear spin of atoms. This work led to his being awarded the Nobel Prize for Physics in 1944. Nuclear magnetic resonance became an important tool for nuclear physics and chemistry. The subsequent development of magnetic resonance imaging from it has made it important to medicine as well. During World War II, he worked on radar at the Massachusetts Institute of Technology Radiation Laboratory and on the Manhattan Project. After the war, he served on the General Advisory Committee of the Atomic Energy Commission, and was chairman from 1952 to 1956. He also served on the Science Advisory Committee of the Office of Defense Mobilization, and was science advisor to President Dwight D. Eisenhower. He was involved with the establishment of the Brookhaven National Laboratory in 1946, and later, as United States delegate to UNESCO, with the creation of CERN in 1952. When Columbia created the rank of university professor in 1964, Rabi was the first to receive such a chair. A special chair was named after him in 1985. He retired from teaching in 1967 but remained active in the department, and held the title of University Professor Emeritus and Special Lecturer until his death. Early years. Israel Isaac Rabi was born on 29 July 1898 into a Polish Jewish Orthodox family in Řymanice, Galicia, in what was then part of Austria-Hungary, but is now Poland. Soon after he was born, his father, David Rabi, emigrated to the United States. The younger Rabi and his mother, Shindel, joined David there a few months later, and the family moved into a two-room apartment on the Lower East Side of Manhattan. At home the family spoke Yiddish. When Rabi was enrolled in school, Shindel said his name was Izzy, and a school official, thinking it was short for Isidor, put that down as his name. Henceforth, that became his official name. Later, in response to anti-Semitism, he started writing his name as Isidor Isaac Rabi, and was known professionally as II. Rabi. To most of his friends and family, including his sister Gertrude, who was born in 1903, he was known simply as Rabi, which was pronounced Robbie. In 1907, the family moved to Brownsville, Brooklyn, where they ran a grocery store. As a boy, Rabi was interested in science. He read science books borrowed from the public library and built his own radio set. His first scientific paper, on the design of a radio condenser, was published in Modern Electrics when he was in elementary school. After reading about Copernican heliocentrism, he became an atheist. "It's all very simple," he told his parents. Who needs God? As a compromise with his parents, for his bar mitzvah, which was held at home, he gave a speech in Yiddish about how an electric light works. He attended the Manual Training High School in Brooklyn, from which he graduated in 1916. Later that year, he entered Cornell University as an electrical engineering student, but soon switched to chemistry. After the American entry into World War I in 1917, he joined the Students' Army Training Corps at Cornell. For his senior thesis, he investigated the oxidation states of manganese. He was awarded his Bachelor of Science degree in June 1919, but since at the time Jews were largely excluded from employment in the chemical industry and academia, he did not receive any job offers. He worked briefly at the Ledley Laboratories, and then as a bookkeeper. Education. In 1922 Rabi returned to Cornell as a graduate chemistry student, and began studying physics. In 1923 he met Helen Newmark, a summer semester student at Hunter College. They began courting, and in order to be near her when she returned home, Rabi continued his studies at Columbia University, where his supervisor was Albert Wills. In June 1924 Rabi landed a job as a part-time tutor at the City College of New York. Wills, whose specialty was magnetism, suggested that Rabi write his doctoral thesis on the magnetic susceptibility of sodium vapor. The topic did not appeal to Rabi, but after William Lawrence Bragg gave a seminar at Columbia about the electric susceptibility of certain crystals called Tutton's salts, Rabi decided to research their magnetic susceptibility, and Wills agreed to be his supervisor. Measuring the magnetic resonance of crystals first involved growing the crystals, a simple procedure often done by elementary school students. The crystals then had to be carefully prepared by skillfully cutting them into sections with facets that had a different orientation to that of the internal structure of the crystal, and the response to a magnetic field had to be painstakingly measured. While his crystals were growing, Rabi read James Clerk Maxwell's 1873 treatise on electricity and magnetism, which inspired an easier method. He lowered a crystal on a glass fiber attached to a torsion balance into a solution whose magnetic susceptibility could be varied, that was between two magnetic poles. When it matched that of the crystal, the magnet could be turned on and off without disturbing the crystal. The new method was not only much less work, it also produced a more accurate result. Rabi sent his thesis, entitled On the Principal Magnetic Susceptibilities of Crystals, to Physical Review on 16 July 1926. He married Helen the next day. The paper attracted little fanfare in academic circles, although it was read by Karya Manikam Srinivasa Krishnan, who used the method in his own investigations of crystals. Rabi concluded that he needed to promote his work as well as publish it. Like many other young physicists, Rabi was closely following momentous events in Europe. He was astounded by the Stern-Gerlach experiment, which convinced him of the validity of quantum mechanics. With Ralph Kronig, Francis Bitter, Mark Zemansky and others, he set out to extend the Schrödinger equation to the symmetric top and find the energy states of such a mechanical system. The problem was that none of them could solve the resulting equation, a second-order partial differential equation. Rabi found the answer in a book by the 19th-century mathematician Carl Gustav Jacob Jacobi. The equation had the form of a hypergeometric equation to which Jacobi had found a solution. Kronig and Rabi wrote up to their result and sent it to Physical Review, which published it in 1927. Europe. In May 1927, Rabi was appointed a Barnard Fellow. This came with a $1,500 stipend for the period from September 1927 to June 1928. He immediately applied for a year's leave of absence from the City College of New York so he could study in Europe. When this was refused, he resigned. On reaching Zurich, where he hoped to work for Erwin Schrödinger, he met two fellow Americans, Julius Adams Stratton and Linus Pauling. They found that Schrödinger was leaving, as he had been appointed head of the Theoretical Institute at Friedrich Wilhelm University in Berlin. Rabi therefore decided to seek a position with Arnold Sommerfeld at the University of Munich instead. In Munich, he found two more Americans, Howard Percy Robertson and Edward Condon. Sommerfeld accepted Rabi as postdoctoral student. Rudolf Peels and Hans Bethe were also working with Sommerfeld at the time, but the three Americans became especially close. On Willer's advice, Rabi travelled to Leeds for the 97th annual meeting of the British Association for the Advancement of Science, where he heard Werner Heisenberg present a paper on quantum mechanics. Afterwards, Rabi moved to Copenhagen, where he volunteered to work for Niels Bohr. Bohr was on vacation, but Rabi went straight to work on calculating the magnetic susceptibility of molecular hydrogen. After Bohr returned in October, he arranged for Rabi and Yoshio Nishina to continue their work with Wolfgang Pauli at the University of Hamburg. Although he came to Hamburg to work with Pauli, Rabi found Otto Stern working there with two English-speaking postdoctoral fellows, Ronald Fraser and John Bradshaw Taylor. Rabi soon made friends with them, and became interested in their molecular beam experiments, for which Stern would receive the Nobel Prize in Physics in 1943. Their research involved non-uniform magnetic fields, which were difficult to manipulate and hard to measure accurately. Rabi came up with the idea of using a uniform field instead, with the molecular beam at a glancing angle, so the atoms would be deflected like light through a prism. This would be easier to use, and produce more accurate results. Encouraged by Stern, and greatly assisted by Taylor, Rabi managed to get his idea to work. On Stern's advice, Rabi wrote a letter about his results to Nature, which published it in February 1929, followed by a paper entitled Zur Methode der Ablenkung von Molekularstrahlen zur Zeitschrift für Physik, where it was published in April. By this time the Barnard Fellowship had expired and Rabi and Helen were living off a $182 per month stipend from the Rockefeller Foundation. They left Hamburg for Leipzig, where he hoped to work with Heisenberg. In Leipzig, he found Robert Oppenheimer, a fellow New Yorker. It would be the start of a long friendship. However, Heisenberg departed for a tour of the United States in March 1929, so Rabi and Oppenheimer decided to go to the ETH Zurich, where Pauli was now the professor of physics. Rabi's education in physics was enriched by the leaders in the field he met there, which included Paul Dirac, Walter Heitler, Fritz London, Francis Wheeler-Loomis, John von Neumann, John Slater, Leo Szilard and Eugene Wiener. Molecular Beam Laboratory. On 26 March 1929, Rabi received an offer of a lectureship from Columbia, with a good annual salary of $3,000. The Dean of Columbia's Physics Department, George B. Pegram, was looking for a theoretical physicist to teach statistical mechanics and an advanced course in the new subject of quantum mechanics, and Heisenberg had recommended Rabi. Helen was now pregnant, so Rabi needed a regular job, and this job was in New York. He accepted, and returned to the United States in August on the SS President Roosevelt. Rabi became the only Jewish faculty member at Columbia at the time. As a teacher, Rabi was underwhelming. Leon Lederman recalled that after a lecture, students would head to the library to try and figure out what Rabi had been talking about. Irving Kaplan rated Rabi and Harold Urey as the worst teachers I ever had. Norman Ramsey considered Rabi's lectures pretty dreadful, while William Nierenberg felt that he was simply an awful lecturer. Despite his shortcomings as a lecturer, his influence was great. He inspired many of his students to pursue careers in physics, and some became famous physicists. Rabi's first daughter, Helen Elizabeth, was born in September. A second girl, Margaret Joella, followed in 1934. Between his teaching duties and his family, he had little time for research, and published no papers in his first year at Columbia, but was nonetheless promoted to assistant professor at its conclusion. He subsequently became a professor in 1937. In 1931, Rabi returned to particle beam experiments. In collaboration with Gregory Bright, he developed the Bright-Rabi equation, and predicted that the Stern-Gerlach experiment could be modified to confirm the properties of the atomic nucleus. The next step was to do so. With the help of Victor W. Cohen, Rabi built a molecular beam apparatus at Columbia. Their idea was to employ a weak magnetic field instead of a strong one, with which they hoped to detect the nuclear spin of sodium. It was predicted that if the nuclear spin were A, then the magnetic field would split the beam into beamlets. When the experiment was conducted, 4 beamlets were found, indicating that the nuclear spin of sodium was 3/2. Rabi's molecular beam laboratory began to attract others, including Sidney Millman, a graduate student who studied lithium for his doctorate. Another was Gerald Zacharias, who, believing that the sodium nucleus would be too difficult to understand, proposed studying the simplest of the elements, hydrogen. Hydrogen's deuterium isotope had only recently been discovered at Columbia in 1931 by Urey, who received the 1934 Nobel Prize in Chemistry for this work. Urey was able to supply them with both heavy water and gaseous deuterium for their experiments. Despite its simplicity, Stern's group in Hamburg had observed that hydrogen did not behave as predicted. Urey also helped in another way. He gave Rabi half his prize money to fund the molecular beam laboratory. Other scientists whose careers began at the Molecular Beam Laboratory included Norman Ramsey, Julian Schwinger, Jerome Kellogg and Polycarp Kusch. All were men. Rabi did not believe that women could be physicists. He never had a woman as a doctoral or postdoctoral student, and generally opposed women as candidates for faculty positions. At the suggestion of C. J. Gorter, the team attempted to use an oscillating field. This became the basis for the nuclear magnetic resonance method. In 1937, Rabi, Kusch, Millman and Zacharias used it to measure the magnetic moment of several lithium isotopes with molecular beams, including LiCl, Lif and dilithium. Applying the method to hydrogen, they found that the moment of a proton was 2.785 plus or minus 0.02 nuclear magnetons, and not 1 as predicted by the then-current theory, while that of a deuteron was 0.855 plus or minus 0.006 nuclear magnetons. This provided more accurate measurements of what Stern's team had found, and Rabi's team had confirmed, in 1934. Since a deuteron is composed of a proton and a neutron with aligned spins, the neutron's magnetic moment could be inferred by subtracting the deuteron and proton magnetic moments. The resulting value was not 0, and had sign opposite to that of the proton. Based on curious artifacts of these more accurate measurements, Rabi suggested that the deuteron had an electric quadrupole moment. This discovery meant that the physical shape of the deuteron was not symmetric, which provided valuable insight into the nature of the nuclear force binding nucleons. For the creation of the molecular beam magnetic resonance detection method, Rabi was awarded the Nobel Prize for Physics in 1944. World War II. In September 1940, the British TIS mission brought a number of new technologies to the United States, including a cavity magnetron, a high-powered device that generates microwaves using the interaction of a stream of electrons with a magnetic field. This device, which promised to revolutionize radar, demolished any thoughts the Americans had entertained about their technological leadership. Alfred Lee Loomis of the National Defense Research Committee decided to establish a new laboratory at the Massachusetts Institute of Technology to develop this radar technology. The name Radiation Laboratory was chosen as both unremarkable and a tribute to the Berkeley Radiation Laboratory. Loomis recruited Lee Dubridge to run it. Loomis and Dubridge recruited physicists for the new laboratory at an Applied Nuclear Physics Conference at MIT in October 1940. Among those who volunteered was Rabi. His assignment was to study the magnetron, which was so secret that it had to be kept in a safe. The radiation laboratory scientists set their sights on producing a microwave radar set by the 6th of January 1941, and having a prototype installed in a Douglas A-20 Havoc by March. This was done, the technological obstacles were gradually overcome, and a working microwave radar set was produced. The magnetron was developed to permit a reduction in wavelength from 150 cm to 10 cm, and then to 3 cm. The laboratory went on to develop air-to-surface radar to detect submarines, the -584 Seychelles rupees radar, a fire control system, and LORAN, a long-range radio navigation system. At Rabi's instigation, a branch of the radiation laboratory was located at Columbia, with Rabi in charge. In 1942, Oppenheimer attempted to recruit Rabi and Robert Bacher to work at Los Alamos on a new secret project. They convinced Oppenheimer that his plan for a military laboratory would not work, since a scientific effort would need to be a civilian affair. The plan was modified, and the new laboratory would be a civilian one, run by the University of California under contract from the War Department. In the end, Rabi still did not go west, but did agree to serve as a consultant to the Manhattan Project. Rabi attended the Trinity test in July 1945. The scientists working on Trinity set up a betting pool on the yield of the test, with predictions ranging from total dud to 45 kilotons of TNT equivalent. Rabi arrived late and found the only entry left was for 18 kilotons, which he purchased. Wearing welding goggles, he waited for the result with Ramsey and Enrico Fermi. The blast was rated at 18.6 kilotons, and Rabi won the pool.